to 1308 web series. This is now Chapter 2. Chapter 2 is an interesting one because it involves the chemistry of biology. It is one of the most difficult topics because chemistry is something that is difficult to understand in addition to understanding the biology. So these lecture videos will be very helpful starting with Chapter 2, the chemistry for biology. Next slide. Now this is showing you that the change in the temperature, the change in the chemistry of the oceans can cause the death of the coral reefs. If you remember recently, there was a big temperature change in Florida, off the coast of Florida, and many of the reefs there died because the temperature of the water and the chemistry of the water had changed. Okay, this slide I don't care. This one I don't care. This one I do care. Now, as I've mentioned in Chapter 1, Chapter 2 relies on flashcards as well. So you'll need to know the definitions that you see on the screen. The definition of matter, the mass, and then the element. Now keep in mind that mass is actually the amount of the substance. It's not the same as weight. Weight is because of gravity, but mass is always constant. Weight can change. Your weight on Earth, your weight on the moon is different because of gravity's effect. So weight is always going to change, but mass will never change because it is the amount of the material. So that distinction is often helpful. So mass is what you're made out of, is the amount of material that you're made out of. Weight will vary depending on whether you're on Earth or on another planet like the moon or whatever, all because of gravity. So weight is different. All right, then we have element. Now element cannot be broken down. It's one of the lowest denominators, and they do involve chemical reactions. So, okay, they can't be broken down any further, and they are dealing with chemical reactions. Now you are going to see a slide that says what are elements made out of, but in the end it doesn't mean that elements are broken down any further because they can't be broken down any further, but elements have subparts, and we'll talk about that in a little while. And as it says down here, all matter is composed of elements. So on the periodic table, which is my next slide, on the periodic table we have the periodic table of elements, and you can see all of them listed here, and these are the known elements on the planet. Now the way this chart works, you do not have to memorize this chart, but it is important to know certain things that will be asked for. For example, they have picked one element here. They picked carbon. So carbon is an element that they've picked. And notice there's a number at the top, but it has two possible definitions. The atomic number for carbon is 6, but at the same time, the number of protons is also 6. Now, that is always fixed for a given element. So all of these on the periodic table that you see have a fixed number of atomic number, and they have the same fixed number of protons. Okay, so that's what carbon, in carbon's case, it's 6. Then we have the mass down here, and for carbon, the mass is 12.01, and that's going to be in grams. Again, you do not have to memorize the periodic table, but you need to understand that the bottom number mentioned here is in grams. So one carbon weighs 12 grams, and that's what this slide is saying, that carbon weighs 12 grams for one carbon. Now, the other thing we want to get out of this is that each one of these on the periodic table, as I said, has a different atomic number, and they're laid out that way. So for example, hydrogen being first on the list, the hydrogen's atomic number is 1. So therefore the number of protons that hydrogen has is also 1. So hydrogen has the atomic number 1, and it has the number of protons 1. If I scoot over to the right where I see helium, He, helium has an atomic number of 2, so the number of protons would be 2 as well. Now the mass is not listed here, not material, as long as you know that if you do see a chart that the mass is given to you, you know that that mass would be weighed in grams. Now, on a test purpose kind of thing, what I would do is I'll give you some examples of how this will be asked on a test. So what if I told you that I'm looking for oxygen, which is over here on the right? And oxygen happens to have the atomic number 6. So oxygen's atomic number is 6. So what would that say in terms of the number of protons? If the atomic number is 6, then the number of protons must also be 6. What if I told you that the weight, the mass, is 16? So the mass for oxygen would be 16 grams. So one oxygen weighs 16 grams. So keep that illustration in mind. So we're still on oxygen. So oxygen's atomic number is 6. Therefore, the number of protons is also 6. And I gave you that the mass was 16, which means it translates that the mass is going to be 16 grams. Now, there's something else I want to introduce here, and that's called the number of neutrons. So neutrons are something else we'll see on an upcoming slide. Now, neutrons plus protons makes up the mass. So the mass, so this 12 right here, this 12, well, that 12 is because it took the number of protons and the number of neutrons, and it came up with the number 12. So if I were to work out the number of neutrons for carbon, it would also be 6 because 6 plus 6 makes 12. So the number of neutrons is always going to be decided by subtracting the mass from the number of protons, and that will give you the number of neutrons. So another way to say it is that neutrons plus protons make up the mass. And in this example, 6 being the number of protons, 6 being the number of neutrons, that's how you got the mass of 12 here. Let's try another one to make sure we're clear. The next one I want to try is chlorine that you see over here on the far left as a picture. And chlorine happens to be over there on the right, but the picture is on the left here. So chlorine, its number of proton is 17. Okay, 17, that's the number of protons, and it's also the atomic number. So chlorine has a protons of 17 and the atomic number of 17. Now what if I told you that it weighs 35 grams? So now we have the following. We have 17, which is the atomic number, which is also the number of protons, and then we have the mass, which is 35. And I want to know how many neutrons. And I just told you that the protons and the neutrons added together make the mass. So how would I figure out the number of neutrons? Well, I would take the mass of 35, subtract it from 17, and that's going to give me 18 neutrons. Okay, so 17 protons, 18 neutrons adds up to the mass of 35 grams because protons and neutrons make up the mass. Okay, next slide. Okay, on this slide, I care for this line down here where it says compounds. So you can actually put elements together, and that makes a compound. So like H2O, that's water, right? H2O is water. Well, that's a compound because it's hydrogen and oxygen put together in a certain way, right? Then we have carbon dioxide, which is carbon and oxygen put together in a certain way. Those are compounds. When elements are put together in a certain ratio, they're called compounds. Now, not listed here, but you need to know this for the test because people ask it, and that is what are the 4 main elements? And that's this line right here where it says 4 main elements. And what are they? Well, those are called CHON, and that's C-H-O-N. C-H-O-N. And that stands for carbon, hydrogen, oxygen, and nitrogen. So most of the animals, most of life on the planet, requires these 4 elements. So your carbohydrates, your proteins, your lipids, your fats that you take, they're all based on these four elements. Your amino acids, your DNA, they're all based upon these four. So it's carbon, hydrogen, oxygen, nitrogen. Okay, next slide. Don't care for that one. Don't care. Okay, this slide I do care. This slide tells you about the word atom. Atom is a part of the element. So if you have carbon, carbon does have atoms that make it. And within the atoms, we have those three that we just talked about. Protons are part of it. And these are sometimes called subatomic particles, as you see right here. So atom is the smallest unit of matter, but it still is part of the element. Okay, so it's still an element, but the smallest part of that element is called an atom. And atoms are broken down into these three. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. So one more time, protons are positive, electrons are negative, and neutrons are neutral. Now remember I told you a moment ago in the other slide that protons and neutrons make up the mass. How much does an electron weigh? Nothing. It's zero. So the weight of an electron is zero. What does it look like? It looks like this. So here we have the nucleus. That's the center. And in the center, you see the two that we talked about. Protons being positive and neutrons being neutral. And that's why you see that the author says protons and neutrons, and they make up the mass. The electrons, which weigh zero, are pretty much flying around the outside. They call them orbits. So just like orbiting the sun or orbiting the earth, these electrons are going round and round the atom. Okay, and they're orbiting the atom. Okay, next slide. Okay, now we have this slide. Now, the top part I already told you. The number of protons is the element's atomic number. So that's what we did earlier. So for oxygen, the atomic number was 6, so therefore the number of protons was 6. I also told you that the mass comes from what two things? Protons and neutrons make up the mass. So protons, neutrons make up the mass. Now, there is such a thing as an isotope, which is my next comment down here. An isotope is a variation of an element. So let's go back to carbon story. There are actually two kinds of carbons out there. One is called carbon 12 because it weighs 12 grams, but there's another carbon out there called carbon 14. Yes, it's the same carbon 14 that they use for radioactive dating, things like dinosaurs and all of that. Now, the way we do the math, like we did earlier, is this. If the atomic number is always 6 for carbon, and it's always 6 for carbon for the other version as well, but notice that now the masses are different. And if the masses are different, then what's going to also be different? The number of neutrons will be different. So if the carbon's weight is 12, 12 minus 6 will give me 6 neutrons if the weight is 12. But if carbon's weight is 14 and the atomic number still for carbon stays as 6, 14 minus 6 means that I now have 8 neutrons. So as you can see that when the weight changes, remember the mass, when the weight or the mass changes, what's also going to change? The number of neutrons. So when the mass changes, the number of neutrons will be changing because protons never change, right? Protons always are fixed because that's their atomic number. So if the protons and neutrons make up the mass and the mass changes, then by default it means that the neutrons have to change as well. So if the carbon is 12, then the neutrons will be 6. If the carbon's 14, then the neutrons will be 8. Okay? All right, that's important. Next slide. Okay, don't care. Don't care. Okay, chemical bonds, I do care. Now remember, The only thing that really changes in chemical reactions here are only the electrons that play the role. So when it comes to chemical reactions, it's really going to be the electrons that play a role. Now, there are several choices here. You can actually transfer the electrons to someone else, and that's going to be called an ionic bond, which we'll see in a moment. An ionic bond will actually transfer the electrons. Then we have another kind of bond that's called covalent bond, and they're the ones that share electrons. So you can either share electrons or you can transfer them in the case of ionic bonds, and that's what we're about to see. That's how things are held together. So carbon dioxide, water with H2O, they're held together by certain kinds of bonds. Here's the first one that we looked at. The first bond I mentioned was ionic. This is where we are actually gaining or losing electrons. So when we gain or lose electrons, that's an ionic bond. So one item gives away an electron, whereas something else picks up an electron. And we'll see a picture in just a moment. So here's an example. This is table salt, sodium and chloride, table salt. The way table salt stays together as a crystal, as a thing, it stays together because sodium wants to give away one electron and chlorine wants to gain an electron. Now, the goal is to have the even number of electrons on the outside. So their goal is to want to have the even number. So as you can see here, they got 2, 4, 6, 8, 2, 4, 6, 8. They like to have full shells on the outermost. So by having a full shell, they're now happy, but they're happy together by doing what? Sodium loses an electron, chlorine gains an electron, and that's called an ionic bonding. Now, before I go any further, certain things don't like to join with others. Like in this example here, they are. But if I go back to the periodic table, the ones on the far right, like helium, neon, argon, krypton, xenon, radon, these are called noble gases. Why are they called noble gases? Because they walk as if they have their nose held up high, like a noble person, and they don't react with anything else. Let's take an example, a real life one. This is helium. That's what we have in our party balloons, no problem. But then on the far left, we have hydrogen. Hydrogen has one proton, which it likes to readily give to somebody else. Whereas helium has two in the outermost. Remember, helium's atomic number is 2. And since it has an even full shell on the outermost, it doesn't want to react with anything. So a party balloon filled with helium, when you pop a helium balloon, it doesn't do anything. It doesn't react with the air outside. You try that with a hydrogen balloon, like if you ever remember your history of the Hindenburg that finally made it. It was a Zeppelin, Nazi Germany kind of blimp that had hydrogen in it, and they brought it over to the United States. And when it was trying to dock, at that time, something ruptured the balloon, filled with hydrogen. It reacted with the outside air, and it exploded. When I was an undergrad, my college professor did the same thing. Had a huge balloon filled with hydrogen. He took a long pole and popped it, and it exploded. And you can even see the flames shoot out and everything. Because hydrogen is on this side, it wants to give away a proton. It's positively charged, and therefore it wants to react. So everything on the left side here loves to react. Everything on the very last column, helium, neon, argon, krypton, xenon, radon, these are called noble gases. They don't want to react with anything. So that's why when we were on this picture a moment ago, these like to transfer electrons. They're highly reactive. Sodium by itself, you put sodium in water, it will explode. So it's very, very dangerous. Okay, moving on. The next time, the other one I mentioned, the other type, it was covalent. This is where they share. And notice it's among the strongest bonds. So they share electrons. They work together. They share electrons. So here's a picture of that. So here's an example of a covalent bond where we have, and this is formaldehyde, but we have carbon and oxygen bound together here with a covalent bond. Okay, so a covalent bond, and that's what this one would be, a covalent bond. So they're very, very strong bonds, very, very strong. The other reason why this picture is given, because there's another purpose to this picture, is to show you that the shape is based upon the bonding, these sticks that you see here. So each element has a certain shape that it takes on. And why is the shape important? If you remember from chapter 1, I'd mentioned something in chapter 1 that said one of the themes we have in biology is by changing the shape, it changes the function. So in this case, this thing here is formaldehyde, and it actually has a certain shape. By changing that shape, it would turn into something else, and it would have different characteristics. So shape goes with that. So structure, shape, and function. Okay, the next slide is hydrogen bonds. This is the one that goes with water. Now, it is a covalent bond that you see here, covalent bond within water. Okay. So water is a very polar idea, and we'll see that in a second on the next slide. Water is very polar, so one side tends to be positive, one side tends to be negative. Okay, so there is actually a reason for that, and that's why water conducts electricity, right? You don't want to be out in the rain when there's electricity, lightning's going off. Lightning bolt, electricity, not a good thing, right? And with water. So you see that water is conductive because water is polar. There's actually a sidedness to it, which you'll see in the next picture. Okay, so hydrogen bonds hold water together. They hold water together. They also hold other water together with it, which we'll see in a moment on the next slide. Here it is. So over here in this picture, we see hydrogen bonding holding two different waters together. Look carefully. We see the red. The red is oxygen. The oxygen of one water molecule is attracted to the hydrogen of the other water molecule. Why? Because oxygen is slightly negative, and hydrogen, as we said earlier when I said it has a lot of protons, of that one proton, well, hydrogen has that one proton making it positive. So hydrogen is attracted to the oxygen, and that's held by hydrogen bonds. Now these others, meaning within the water, that's going to be a covalent, again, it will be a polar covalent bond. Let me back up on that slide. You'll see it. Okay, so the water is going to be a polar covalent bond. That means it has a little bit of ionic, a little bit of covalent, so it's called polar covalent. And that's what they mean here, where they're saying within that structure, you have hydrogen being more positive, oxygen being more negative. So it's polar covalent within the water molecule. So polar covalent within the water molecule, but hydrogen bonding between the waters. Okay, so hydrogen bonding between the waters. So here's one water, here's another water. That's hydrogen bonding. Okay, next slide. Okay, this is just a question that they ask. I'll move on. Okay, now comes this slide. And this slide is best understood as chemical reactions. You start with something called reactants, and you end up with something called products. That is one that's often missed. I still can't understand why. Reactants are what you start with. Products are what you end up with. Okay? And notice it says here, it can rearrange matter, but it cannot create nor destroy matter. That means you can't make something out of nothing, and you cannot come up with something from nothing. You have to have some starting material, and that starting material is going to change structure, shape, and form, and eventually give you some other chemical. Okay, I don't care. Oops, went too fast. Let me back up. Okay. This is actually a repeat from chapter 1. So this author likes to throw in the themes from chapter 1. So just a slide there. Okay, we now know that water pretty much occupies most of the earth, right? So water occupies most of the earth. But at the same time, we are also mostly made out of what? Water. So most of our blood is water. When I teach that in my upper level courses of A&P2, we teach that water makes up about maybe 89% of our plasma, our blood. So yeah, most of our blood is water, most of our body's water, and most of the earth is water. And why? Because water has certain unique characteristics, which we're going to see. And remember, the polarity of that water molecule and how water molecules bind to other water molecules with hydrogen bonding plays an important role. Okay, so here's your first property of water. The first property of water is cohesion, and that's how water sticks to surfaces. So if you've got water trickling down your glass, like condensation, and water's trickling down your glass, notice it forms like a little water droplet and it rolls down the side of your container. So cohesion is water's ability to stick to each other, and adhesion, which is my next word. So cohesion is when water sticks to itself, because it does. Water sticks to itself. I'll show you that in an example in a moment. But water sticks to itself, and that's cohesion. And when water sticks to a surface, like the glass that I mentioned a second ago, that's adhesion. This author is combining both. That's why I want to give you those two separate terms. So cohesion is when water sticks to itself, and adhesion is when water sticks to a surface, like the side of a container. Now, cohesion has this example. If you put a drop of water on a penny and put another drop of water on the same penny next to the first drop, when you move the penny and the two water droplets touch each other, they become one droplet, correct? Well, that's because of cohesion, where water likes to stick to itself. Okay, so when water sticks to itself, that's cohesion. When water sticks to the side of a container, when it sticks to the side of a container, that's adhesion. Okay, another property of water, and again, I'm breaking these down into pieces. The next property of water is surface tension. Surface tension. And the best example of that is a bug, an insect called a water strider. And that insect actually runs and walks on water. How's it able to do that? Because the insect is so light, and an insect has, of course, the 6 legs, and the legs are barely able to press into the water because the bonds of water holding to each other, that cohesion thing I mentioned, it's so strong that it actually holds up the insect, called the water strider. And that's because of surface tension. Surface tension really holds the water molecules. If you put your finger on the surface of a glass of water, just on the surface, you'll see that it likes to stick to that finger before you can actually press it down further down. So surface tension is very, very good at holding water together. Okay, so that's high surface tension. The next property of water that I need for the test is this. The next property of water is high specific heat. So high specific heat. Now what does that mean? Water does not like to change states unless you give it a lot of energy. So if you're making spaghetti and you boil the water on the stove and the water's now boiling because you put a lot of energy in to boil the water, and then you change your mind and you turn the stove off, you know that that water doesn't immediately cool down when you turn the stove off. That's because you put so much energy in to change the liquid water into a gas that it's now starting to bubble and boil, and it's going to take a lot of energy to be released before that water that's boiling and bubbling comes back from gas down into condensation and comes back to liquid again. So that's called high specific heat. Now, why do we have that as a special property for water? That's because if water easily boiled and easily changed state from liquid to gas, even the slightest fever would do what? Would provide enough energy for the water in our body. Remember, I just told you a moment ago, there's a big chunk of our body that's water. So that water and that fever would immediately start to boil our water. And that's what would happen if we were on another planet where things were different. Well, yes, if water did not have that same property, then water would immediately boil from a liquid to a gas. And then that's because of the high specific heat that it doesn't happen. Water takes a lot of energy before it changes state. Okay? Okay, the next one you need to know about, again, properties of water, is water acts as a lubricant. So water will act as a lubricant. Your joints, for example, have water because you need water as a lubricant in your body. Okay, so these are parts of properties of water. Okay, moving on. Okay. Here's your spider. It's not the water strider, but it's a spider, and it does the same kind of thing. As you can see, the legs of the spider are not breaking the surface of the water. The water wants to hold close to each other, and it's actually holding the spider up. So the water's actually holding the spider up because of that nice hydrogen bonding between the waters, that nice little surface tension that we have here. Okay, next, moving on. I already mentioned this. This is just a reverse way of saying the same thing I did about the high specific heat. That's what this is going to. That means because water has a high specific heat, it's going to take a lot of loss of energy before you can cool down. So it says it right here, right there. Conversely, when water cools and you start forming the hydrogen bonds again, it requires a lot of release of heat. So if you want something boiling to come down to cooling and back to liquid again, you're going to have to release a lot of heat. That's why boiling water or steam will burn more than hot water. So never mess with steam because it's hotter than just regular water or hot water. All right, moving off. I'll keep going. You can see this guy's head has a lot of heat coming off of it. Okay, keep moving. Now comes ice. Now, I'm pretty sure everyone knows this, that ice is actually floating because it has a larger surface area inside of it. It's less dense. So you can see here, ice floats because it is less dense than water. Okay? So ice has a more lattice structure, which you'll see on the next slide, and here it is. So you can see ice has a more lattice structure. That's what they call this, a lattice structure. And they take on a certain form for the hydrogen bondings. And therefore ice is going to be less dense and then it's going to float. Liquid water is more solid. More bonds are put together tighter. This is not so tight. If it was a gas, it would even be more loose. The molecules will be bouncing away from each other even more so because there's more kinetic energy moving it because of the heat. Okay, now this slide is very important on the test. Everybody will ask it. So we have a solution here, and the solution is going to have two parts. The thing that you're dissolving is called the solute, and the thing that's doing the dissolving is called solvent. The best way to remember it is this. Kool-Aid mix, the Kool-Aid powder. The Kool-Aid powder is solute, and the water that you're adding to make the Kool-Aid punch is the solvent. And water is usually the universal solvent. And that's what this last line down here is saying. That usually water is the universal solvent. So solute is the powder, the mix, and the liquid, typically water being the solvent. Next slide. So in this picture here, we have sodium chloride. That is the solute. And then the water that it's dissolved in is the solvent. Okay, again, the author is throwing the same overall theme slide in from chapter 1. He'll be doing that in other chapters as well. Okay, the next one is acids and bases. Now, best way to understand an acid is that it releases hydrogen ions. The more hydrogen ions it has to release, the more acidic it is. So, very, very acidic, like the stomach acid example. Stomach acid is pH 2. Why is it pH 2? Because it has a lot of hydrogen ions to release. Something that has a base is the other way around. A base has more hydroxide, and hydroxide is OH. So it has more hydroxide and it has less hydrogen ions. So more hydroxide. So a base that has more OH or more hydroxide, OH. Then we have a pH scale. Now the pH scale is log scale, and I'll explain that on the next slide. It's a log scale. And it always measures the amount of hydrogen ion. That's what it's really doing. It's measuring the amount of hydrogen ion. The last thing on this slide is a buffer. The purpose of a buffer is to minimize the changes in the pH. So if you were to take an aspirin that's buffered aspirin, that's what they call it, buffered aspirin. Aspirin can be quite acidic and it can cause stomach ulcers. But if you have a buffered aspirin with a special coating, it actually does not release too much acid to your stomach and doesn't etch into your stomach and cause a stomach ulcer. So buffered medicines or buffers are minimizing the changes in the pH. Now speaking of pH, here's the scale. So down here is 0, up there is 14. Between 0 and up to 7, but not including 7. So it's from 0 to 6.9999999. So from 0 up to 7, not including 7, is an acid because it has more hydrogen ions. If I had exactly 7, that would be where hydrogen and hydroxide are the same, and therefore it's neutral. So pH 7 would be neutral, okay, because it has the same number of hydrogen and the same number of hydroxide ions. That bracket simply means concentration. Then if it's greater than 7, then that's a base because it has more hydroxide, and as you can see in the picture, it has more hydroxide or OH and less hydrogen ions. Now on this scale, there's two of them you need to know. One that I keep mentioning over and over, and that's stomach acid. Stomach acid has a pH of 2. That's important. So the pH of 2 for stomach acid. The other one you need to know is the pH of blood, and that's why you see a little blood cell mentioned here. Blood is 7.4, which is slightly basic. 7.4. It'll come in handy later in life or in some other class. So blood pH is 7.4. Now the others that you see here just have a general idea, like grapefruit juice, fruit juices, they tend to be acidic. Milk of magnesia, ammonia, or bleach, they tend to be basic. So have some general idea for the purpose of the test. Now remember, these are log scales. That means that every time I go up from 0 to 1, it's actually a 10-fold difference. So if I were to ask a question on the test, if I go from pH 2 to pH 4, right? pH 2 is acidic, pH 4 is acidic, but I did go and make it a little bit more basic by going from 2 to 4. Well, in doing so, how many times more basic is it now? Remember, every jump is a factor of 10. So if I go from 2 to 3, that's actually 10 times more. If I go from 3 to 4, is another 10 times more. So if I have that question of pH 2 to pH 4, how many times more basic is it now? It's 10 times 10 for every one of those jumps. So it's going to be 100 times more basic when I go from pH 2 to pH 4. If I went the other way, from pH 4 to pH 2, it would now be the same answer, but it would be 100 times more acidic. Okay? So it's a factor of 10. So every time I go up a number, it's a factor of 10. So if I go from 5 to 7, well, that's again 5, 6, 7. That's 2 jumps. So that's going to be 100. Because how many zeros are there in 100? 2. If I went from 5 to 8, that's 3 jumps. If it's 3 jumps, then how many zeros will it have? 3 zeros. So that's 1,000 times. So every jump is a factor of 10. Okay, next slide. This slide here has to do with that whole CO2 building up in the environment thing. So if there's too much CO2 in the environment, it's the ocean's job to convert it to carbonic acid. But here's the problem. If we have the oceans doing the work of taking all that carbon dioxide out of the air and converting it to carbonic acid, it's going to make the ocean water more acidic and start to kill off some of the coral reefs that you see. So yes, the ocean does it, but it can only do so much. You don't want to make the oceans too acidic either. So that's why it's best not to even produce too much CO2. I'll quickly digress to show you that some of this smog problem that we had. During COVID, I have a picture from one of the areas of India in Delhi that has a little photo of the Himalayas and the mountains and everything. And before COVID, you could barely see the mountains through this monument at all because Delhi is very, very polluted and dirty and smog and air pollution. But during COVID, where all of the cars had stopped because people were restricted to homes and shopping and can't be done and all that kind of stuff, they actually showed for the first time in decades where you could actually see the mountains through this monument. So that's why I said the air pollution is a big deal. Okay, moving on. Matter of fact, look what someone asked on the test right here, or this question. Compared with the solution of pH 8, the same volume of solution of pH 5, now we know what? That pH 8 would have what? 1,000, because 8 to 5 is 3 jumps, 1,000 times more hydrogen ions. Okay, so you can see now it's 1,000 more hydrogen ions, which means it's going to be very acidic. Okay, very acidic, going from 8 to 5. So the second solution is going to be quite acidic. The first one was basic at pH 8, and now we're going to pH 5. So we're now 1,000 times more acidic. And that's why I asked such a question earlier. Again, a repeat of the theme. Okay, I don't care about this. This carbon dating is not a big deal for me. So there's the carbon dating story. So when an animal dies, there's a certain amount of carbon-14 in everybody, in each of us. There's a certain amount of carbon-14. And then once you die, that carbon-14 starts dying off as well. So if you find something that's been there long time, you can see that the longer it's been buried and the longer it's been gone away, the less of that carbon-14 will be there. And that's why carbon-14 is nice for dating. So when that body decomposes, some of that carbon-14 goes away, and the less you have, the longer the years have gone by. So the less you have, the longer the years have gone by. So that way you know how many years has it been. Okay? All right, so that's carbon dating. Now that takes care of the 1308 video series for chapter 2. You can now move on to chapter 3.